Okay, we're back. We're going to talk about resonance now. We've talked about lots of different uh, things having to do with the shape of a sound and the amplitude and the frequency and all those things. And now we're going to talk about things that have to do with the richness of the sound, how big the sound is or not, right? So oscillations in a system are produced, maintained, and enhanced by means of periodic transfer of energy from another oscillating system whose frequency is identical to the first system, and that has to do with the environment. Okay, so if we have these other systems that are supportive of what those oscillations are doing, then we're going to see a jump in resonance. We tend to think about resonance as the broadness that we desire in music, and sharp resonant notes are sometimes those notes that sort of jump out at us, and some jump out at us more than others simply because of this idea that you have things in the environment that may be more sympathetic to those vibrations than others. Everything has a degree of resonance. It just has the issue is to what degree, right? And some materials don't resonate nearly as much as other materials, which is why we are able to treat rooms with acoustic treatments. Sympathetic resonance, periodicity, all those things get close to the natural resonating frequency, and what happens is when those things come together, the sound goes, it sort of explodes, right? So let's look at this really cool resonance demonstration. And here's the YouTube, the URL if you want to go to that.
Hi gang, sound time. If this room were filled with ping pong balls and I had a big paddle and I shook it back and forth, I'd send vibrations through those ping pong balls. Same type thing happens when I strike this tuning fork. This vibrates back and forth and hits the air. And the air vibrations, that's what you pick up as sound. Here I have a fork of frequency, frequency, same, same. Watch, listen at me. Strike this one, and this one vibrates. Or, as long as the frequencies are matched, I can get the vibrations to cascade back. It's called resonance. Huh? What happens if this fork has a different frequency? Let's try now. Yuck, nothing. I have to have this frequency the same as this to pick up the vibrations from here. That's what happens with a radio set. Your radio signals are coming in, and you change the frequency of your radio set so that it matches the incoming frequency. You got it. Physics. Yay.
Yay, physics. So, just a real brief demonstration on resonance. One of the coolest demonstrations, I think, having to do with resonance has to do with Chladni Figures. And so just let's real quickly talk a little bit about Ernst Chladni. He was a German physicist and a musician, and in the late 1700s, he drew a bow over a piece of metal whose surface was lightly covered with sand. And when the plate was bowed until it reached resonance. And how did he know that? Well, he started to see patterns form on the plate that just are mind-blowing. The sand formed patterns showing the nodal regions, the resonant areas on that plate, and we call them now Chladni figures. A speaker driven by an electronic signal generator over and under the plates achieves this result as well, and we're going to do this, let you take a look at that in just a second. Here's a bonus box. Chladni also invented a few musical instruments. What are they? How do they work? And do we still use them today? So think about that. Chladni. He also invented a few musical instruments. What are they? How do they work? Do we still use them today? Email me or send me a note via Blackboard to let me know that you're investigating that bonus box. Let's take a look at this video, which gives a really nice, clear demonstration on Chladni figures. Here it is. And as you see those figures form, what you're seeing actually are the resonant points on the plate, points on the plate that resonate with that frequency. The frequency will change. Pretty amazing, isn't it? Absolutely amazing. And beautiful. So there's more video here with better sound. Let's take a look at that real quick here. Fast forward this a little bit here because that goes on for a long time. A little bit more.
33, 38. 38, 35.
Go ahead and add some more.
42, 21.
Add some more, please.
42, 8. Oh, that's cool. Oh, 55, 93. 58, 16. 5907. 07. 7148. And that will be it.
Yeah, so pretty cool stuff. If you want to do that on your own, again, you're going to have access to this in your stuff on Blackboard. All right, so let's take a look at Chladni Figures on a violin. This is one of the ways violins can be tuned, right, as they're being developed. See where the resonance lay. I'm going to stop right there. That gives you a really good idea about Chladni figures and resonance, and it underscores the idea that everything has resonance to some degree. So let's do an activity. Do you resonate? I want you to listen to this C. Right, that's a C. Right, and hum that pitch loudly with your hand on your nose until you feel the mask of your face vibrate. Right. Keep your chin down and also keep down the tension in your throat. Right? Go ahead and do that. Hum again and open your lips to an O without losing resonance. Mo. Then try humming the third, E, and the fifth. Hum more softly and maintain resonance. All right, so you bum bum bum. You're going to hum the triad. All right, and I'm going to ask you. I'm sorry that my picture is in the middle of all this. What are you resonating? Are you resonating your face, your body, the room? Resonators are instruments, bodies, rooms. Resonance is everywhere. It's vibration in any chamber, in anything. So you're resonating lots of things going on inside your body, which is why this is so important to singers. Can you imagine that this resonating chamber sometimes has closed doors when we have allergies or when we have a bad cold? And when we have that going on in our bodies, can't help but make changes in the resonance of our sound. For string instruments, the resonating frequency depends on the length of the string, the composition of the string, tension and thickness of the string, bowing, plucking, and striking all have impact. All have impact. So, does glass resonate? Now, from the conversation we just had, the answer probably should be yes. Does glass resonate? Let's take a look to see if you're right.
Shockwaves from a punch can do damage to the human body. Now we're going to time warp at 10,000 frames per second to see how sound waves destroy glass. Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw...
Okay, I'm going to let you look at the rest of that on your own. So you'll have that link. Go ahead and check it out to see if you are correct in your assumption that glass probably does resonate. We're closing in on the end of this video, so let's talk about a few more ideas about how sound moves. Let's talk first about diffusion. The diffusion is a scattering of sound energy, so it's just very logical. When things diffuse, they move, right? It reduces that sense of localization. So, for example, my husband and I, a few weeks ago, we were actually in a geodesic dome, and I was upstairs and he was downstairs, and he was talking to someone downstairs and wasn't speaking in a very loud voice at all, just a very soft voice. I was upstairs in another area, and it sounded like they were right next to me. So this idea of diffusion, as you can imagine in a geodesic dome, that this sound was bouncing all over the place. It's important for avoiding dead spots in concert halls. So when engineers tool performance spaces, this is one of the things that they think about. The other thing has to do with reflecting. Echoes caused by enclosures, and the enclosure shape has impact, and it goes back to that geodesic dome again. Is the shape round? Is it squared? Is it multi? Are there multi walls? And so in other words, take a look at this group here, and they're singing against a circular wall, but the walls curve this way, and when they sing, that sound bounces outward rather than back at them. Here it might bounce back at them a little bit, but inside that circle, that sound is going to be circulating around those circular walls. Let's take a look at a little reflection video. This is real quick. This is just to demonstrate how sound is reflected, and you can see in this sense it moves off of here and it is reflected in another direction. So we've had diffusion, we've had reflection, and now we're going to talk about refraction, not rarefaction, refraction. So when we talk about refraction, most everybody, I'm assuming, would immediately think of a prism, right? As we put light through a prism, that light is refracted. Refraction basically means bending, right? So as the light comes into a prism, that light is bent so that we can see all the colors. A similar thing happens with sound. We're going to bend the wavefront as it passes through varying densities. Right? The density changes in the air change the direction of the sound wave, and wind functions in the same manner. So if this is the sound source, right, and we're headed towards the listener, right, The warmer the air, the faster the sound speed. The cooler the air, the slower the sound speed. Here is the sound source here. Here's the listener. Here is the bending of sound. This is the direct path. Here is a refracted path. Here is a picture of refraction, in this video I should say. Here comes the sound source. And see how it's bent. One more time. And I think we're getting towards the end here. This is diffraction, right? Diffraction, and in which waves fill in areas. The higher the frequency, the less it's going to be diffracted. So if you have piccolos and tubas, or violins and string basses, think about how those sounds are diffracted in a room. The old Academy of Music with the columns. We have spaces where the waves will try to fill in around the back of the columns, because those columns are going to try to interfere. And here is diffraction. And see how the sound is moving through here and entering into this space. Just another view of that. Okay, so we're at the end of Module 1, and well, the end of the videos for Module 1. It gives you sort of a foundation for all the things we've been talking about. I want you to read the Thompson book, do all the things that I've asked you to do for all the learning activities, and have fun.